Okay, in 15.2, we're going to continue talking about finding antiderivatives and learning different rules. But before I do, I want you to take a few minutes to look at the two integration problems I've posed and think about, with what you know now, how would you integrate each of these problems? I also want you to think about, if they were derivative problems, what rule would you have to use in order to find the derivative of these problems? Well, with what I know now, on this first problem, the only thing I can think of is that I would have to rewrite this out twice. I would have to FOIL it, then I would have to distribute the 2x through before I could actually integrate. Because to me, this looks like a chain rule if this were derivatives. So if I looked at the next problem, if I was doing the second problem, then I would have to rewrite this out 4 times. Okay, yeah, no, we're not going to do that. I wouldn't make you FOIL that out 4 times and distribute the 6x through. There must be an easier way to do these types of problems. If you notice that both of these types of problems to me almost look like chain rule problems if they were derivatives, right? But instead of having to FOIL it out and distribute and do all that work before, let me show you a cool technique that we can use anytime I see what I call a chain rule antiderivative problem. I'm going to take out this inside part and I'm going to call it u. So I'm going to call u x squared plus 1. So now my new problem is u squared. So I took out the x squared plus 1 and I called him u, right? And so now I have a u squared, and then I have times a 2x dx, right? Off to the side, I'm going to take that u and I'm going to find his derivative. I'm going to find the derivative of u with respect to x. So what is the derivative? Not antiderivative. What is the derivative of x squared? 2x, right? And the derivative of 1 is 0? Okay, so the derivative of x squared plus 1 is 2x. Then I'm going to multiply both sides by dx, and that would get rid of the dx on this left side. So now I have an equation that says that du is equal to 2x dx. Oh, and doesn't that kind of look familiar? Doesn't this 2x dx and this 2x dx have the same stuff in it? So in my integration problem, instead of calling that a 2x dx, what is 2x dx equivalent to? Well, didn't we say over here that 2x dx is equivalent to du? So now I'm going to actually take that out and call that du instead. So now look at the nice simplified integration problem that I've just created. I now have an integration or an antiderivative problem that says find me the antiderivative of u squared. Integrate u squared with respect to u. If those were just x's, couldn't you find me the derivative of x squared by using the antiderivative of x squared by using our power rule? Well, that's the same thing we're going to do. It just happens to have u's in it. So what's the antiderivative of u squared? Well, isn't that u cubed over 3? Remember, plus c, my constant of integration? But my answer can't be in terms of u because my question wasn't in terms of u. The question really asked me to anti-differentiate it in terms of x's. And so going back, what did we actually call u in the first place? Well, didn't we call u this x squared plus 1? So now I can back substitute and plug back in my x squared plus 1, and I've just found the antiderivative of my original problem without having to FOIL it all out. I promise you, if you try to take the derivative of that, you would end up getting back what you started. Try it. Make sure you use the chain rule and see if you get the same thing that you started with. Pretty cool, huh? Instead of having to FOIL it out a whole bunch of times. So then do the same thing with this second problem. Look at this second problem. Remember before, we were going to have to FOIL that thing out 4 times, right? And distribute a 6x squared. Instead, can we take out this inside? Can we call it u instead? And really, you can call it whatever letter you want to. They just oftentimes call it u. And so now my new integration problem says u to the 4th times 6x squared dx. Now off to the side, I'm going to find the derivative of u with respect to x. So the derivative of 2x cubed plus 1 is really 6x squared. I'm going to multiply both sides by dx, and I end up getting that du is really 6x squared dx, which is perfect because look at this. 6x squared dx now is the same thing as that du, so I can substitute in a du instead of saying 6x squared dx. So now I have a much more simplified antiderivative problem, an indefinite integral that says u to the fourth. So the antiderivative of u to the fourth using my power rule is u to the fifth over 5, remember, plus c. But I can't write my antiderivative in terms of u's. I really need my antiderivative to be in terms of x's because that's what it asks for in the original problem. So now the last step is to just back substitute. Take what we called u in the first place and plug that back in to my problem. So what did we call u in the first place? Well, that was our 2x cubed plus 1. So my antiderivative is 2x cubed plus 1 to the fifth power over 5 plus c without having to FOIL it out 4 times. It's called U-Substitution. So 15.2 is going to be all about this new technique we're going to use called U-Substitution. We use this technique when you see a chain rule. When you see a chain rule, that's probably our clue that we're going to try U-Substitution. We don't have product rule, we don't have quotient rule, but now we kind of have a technique that we can use when we see a chain rule type of problem.